All right, in this video, we're going to summarize the intermolecular forces and describe some of their applications. So we'll remember that the five different intermolecular forces are the ion dipole force, which as the name suggests is the force between an ion and a dipole or a nonpolar molecule. We also have dipole-dipole forces, which is going to be the force that exists between two polar molecules. Hydrogen bonding, which is a special type of intermolecular force that exists between molecules that contain OH, NH, or FH bonds, and a nitrogen, oxygen, or fluorine on another molecule. And the two more subtle intermolecular forces are the dipole-induced dipole force and the induced dipole-induced dipole forces. Let's use the concept of intermolecular forces to describe why the process of dissolving salt in water, which I can symbolize like this, is endothermic. In other words, the enthalpy change for this is positive. So in order to think about that, we're going to imagine our crystal of sodium chloride, which I'm just going to draw sodium ions and chloride ions, just a couple of them here, attracted to one another like this. And what we would have to imagine for a crystal of sodium chloride to dissolve in water, each of these ions would need to be separated and attracted to a water molecule. So we can designate that something like this. So here the positive sodium ion would be attracted to the partially negative portion of a water molecule in an ion dipole force. And of course, that would need to happen with all of these. I'll just draw two of them here. We could also have this case where a chloride ion would be attracted to the positive portion of a water molecule, which would be the hydrogen atom, and again, an ion dipole force. And for this process to occur, we're going to remember that in order to break these bonds, the bonds between the sodium ions and the chloride ions, that's going to require energy. So our delta H is going to be positive for breaking apart the ions, separating them. And then when this occurs, when the ion dipole force is made, when this particular bond is made, that's going to release energy. Remember, breaking bonds requires energy, while forming them releases energy. And we can see that if the overall process is endothermic, that is, energy is required to drive this overall process, which is the sum of these two processes, we see that for this particular salt, it requires more energy to break apart the ionic crystal than is released when the ion dipole bonds are formed in the solution of the crystal. We can think about this in terms of an equation. We could say the enthalpy change of solution, or the process of dissolving a salt, is going to be the sum of the lattice enthalpy, which is symbolized like this, plus what we'll call the hydration enthalpy. This represents the energy required, which is going to be positive, to break apart the ions, like the sodium ion from the chloride ion. So this is, in a sense, what is the strength of the ion-ion force. So that's this part. And then this part, the hydration enthalpy, this is going to be negative because this represents the attraction, or the bonding, so to speak, between each of these ions and water. And since these associations represent a bonding, when bonds are formed, energy is released. Because the hydration enthalpy involves what we know as an ion dipole force, The interaction between an ion and a dipole, we know that's one of our intermolecular forces. Let's look at some data to gain some insight into what might influence the magnitude or the strength of the hydration enthalpy. Another way of saying this is we're just looking at the strength of attraction between ions and water, which is, again, an ion dipole force. Now, if you look at these interactions here, what you see from left to right is the interaction between lithium and water, sodium and water, potassium and water, cesium and water, and magnesium and water. And below those interactions, you see the relative hydration enthalpies. And we notice that by far, magnesium has the highest hydration enthalpy of all these ions listed. Now, why might that be? It's a pretty simple answer. If you look at the charges, the magnitude of the charges on these ions, magnesium has the highest charge of all these ions. It's +2, whereas the others are all +1. Larger charge, larger strength of attraction between the ion and the dipole. It's going to release more energy when the magnesium and the water come together. So that's going to have the highest hydration enthalpy. That makes sense. If we look at the other ions involved, we see they're all +1, and yet we still see a difference in the hydration enthalpies. Now, what might account for that difference here? If you think about it, what causes a stronger force of attraction between positive and negative charges? If they're all +1, can't be the size of the charge. It's going to be the distance between them. Remember, with electric charge, just like with magnets, the closer you get them together, the stronger the attraction. And so because lithium is smaller than sodium, it can get closer to the water molecule than the sodium ion can. Lithium's going to release more energy and have a more negative hydration enthalpy than sodium. And sodium, which can get closer because it's smaller than potassium, sodium can get closer to water than potassium can. Sodium ion's going to have a more negative hydration enthalpy, a stronger attraction to a water molecule than a potassium ion. And of course, potassium is going to be able to get closer to a water molecule than the cesium ion. And so potassium is going to have a more negative hydration enthalpy than cesium. Stronger attraction leads to more release of energy. Lastly, let's see if we can use our knowledge of intermolecular forces to make sense of the data that we see here. Now, what we're looking at here are boiling points and enthalpy of vaporization of some various substances. Let's look at the top 4 to begin with. They're all nonpolar. And what we're seeing is as the molar mass of the compounds increase, so do the boiling points, and so do the enthalpy of vaporizations. Now this should make sense because, of course, it's going to take more energy to separate larger molecules. But we'll also remember that this concept of polarizability plays a role here. Remember, nonpolar compounds attract one another through induced dipole forces. And this force is impacted by the polarizability, how easily it is to move around the electron cloud of the molecule. And so because as things get larger, as molecules get larger, their polarizability increases. That increases the ability of this electron cloud to shift, which makes it easier to induce a dipole, which leads to stronger attractions. And so it makes sense that the larger the compound, the higher the boiling point, the higher the enthalpy of vaporization. And of course, we see the same trend in the 4 polar compounds below as well. Now, this next comparison is going to take a little bit of thinking to look at. What we're first going to do is we're going to compare the data for nitrogen, which is nonpolar, and carbon monoxide, which is polar. And notice they're very similar. Actually, they're exactly the same in terms of molar mass. Let's compare the boiling points of each of these. We see that carbon monoxide has a slightly higher boiling point, and a slightly higher enthalpy of vaporization than nitrogen. This should make sense. A polar compound, the molecules that make it up, they can undergo dipole-dipole forces, which is a relatively strong attraction. Nitrogen molecules do not have this dipole-dipole force that they can count on, and so therefore the strength of attraction between carbon monoxide molecules is going to be stronger than the strength of attraction between two molecules of nitrogen. And we see this trend continue. If you look at SiH4, the second nonpolar compound, and phosphorus trihydride, the second polar compound, they have similar molar masses, 32 grams per mole versus 34 grams per mole. And yet phosphorus trihydride has a much higher boiling point and a higher enthalpy of vaporization. Again, this dipole-dipole force that polar molecules display that nonpolar molecules do not make it harder to boil, separate into the gas phase, polar molecules as compared to nonpolar molecules. And we see this trend continues. You know, if we look at germanium trihydride and germanium tetrahydride and arsenic trihydride, similar molar masses, but yet the polar compound has a higher boiling point, higher enthalpy of vaporization than the corresponding nonpolar compound of the same molar mass.